Pozdravljeni, bomo kar počasi začeli. Naj se najprej malo predstavim. Jaz sem Mitja Vovk Iskrić, prihajam iz Centralne tehniške knjižnice Univerze v Ljubljani, katera tudi organizira mrežo občanske znanosti. In danes bomo poslušali predavanje, sprejemali vprašanja. Na začetku bi pa malo začeli z predstavitvijo mreže občanske znanosti, da sploh vemo, kje smo in kaj smo. Torej, občanska znanost, upam, da poznate, je koncept znanstveno-raziskovalnega dela, pri katerem sodelujejo lahko vsi. No, v CTK smo v ta namen postavili spletni portal citizenscience.si oziroma občanskaznanost.si, kjer zbiramo projekte občanske znanosti, malo teorije, in smo pač ponosni na to, da smo postavili tale naš katalog projektov, v katerem je kar 86 projektov občanske znanosti, ki na tak ali drugačen način pravzaprav vključujejo javnost v prave znanstvene raziskave. Torej, naša mreža spodbuja tudi take dogodke in predstavitve, kot je tale naš današnji dogodek. Imamo koledar, kjer zbiramo razna poljudno-znanstvena predavanja, ki se dogajajo po Sloveniji ali pa tudi preko Zooma, in smo organizirani v mrežo občanske znanosti. Naši partnerji so že 3 slovenske univerze, znanstveni inštituti, knjižnice, muzeji in drugi, tako da nas je že kar veliko, že 70 nas je, ki sodelujemo v mreži in pravzaprav delamo različne dejavnosti. Pred kratkim smo imeli dan občanske znanosti, ki se je dogajal v Novi Gorici, in so vsi posnetki in prosojnice predavanj tudi na voljo na naši spletni strani, tako da vas vabim, da se pogledate tudi to. Tako da zdaj bi pa povabil kolega Andreja Srakarja, da začne svojo predstavitvijo, potem pa bomo poslušali še predavanje. Hvala.
Najlepša hvala. Hvala za organizacijo tega dogodka, za vse skupaj. Predavanje bo v angleščini, so I will speak in English. Many thanks also to Betsy, Elisabeth Bersson, Dr. Elisabeth Bersson from the University of Massachusetts Institute of Technology, a research group of Professor Tamara Broderick, renowned Bayesian scholar, I would say, and a scholar in data science and machine learning, who will help me in the presentation. So, it will be of about, say, 1 hour, probably maximum time. What we will present is a very novel topic. I will directly say that in considerations ahead of this event, I think it's even brings foundational questions for statistics as such in certain areas of work here. Hopefully we will touch also this. So we will address citizen science firstly as such, present the statistical problems that these approaches bring, data gathering by volunteers, and then walk to the special issue and multi-paper discussion meeting of the Royal Statistical Society that we organized last year, 2 years back. One of the papers was by Betsy and Peter Hoff. There were 2 others, as you will hear. So we will introduce the statistical aspects by going into one earlier article by one of the authors of these 3 articles, Alex, Diana, and co-authors. Then Betsy will present on her article and hopefully also some reflection on this topic, emerging topic also in statistics, as I briefly mentioned. And later I will present other 2 articles and we hopefully conclude with some reflections on the area. So, this I already shortly touched upon. So, citizen science, like Mitja addressed, so in Slovenia we have the network of citizen science, mreža občanske znanosti, which is a, I would say, umbrella cover organization for many projects. Here there was a day of citizen science, I think 2 weeks back in Nova Gorica, and I was quite surprised. Not only Slovenia, Italy, Croatia, Austria, and likely also other countries feature an overload presently of activities. So it's a very intense area of activity, I would say. It has emerged as a novel paradigm in scientific process in recent, I would say, about decade or a bit more. Emergence, the very term citizen science was used for the first time in the late 1980s. First book that theorized the concepts was published in mid-1990s. Since then, interest have grown and is growing. However, one of the interesting features is that it is impossible to define citizen science for all contexts, and there is still not an international consensus about the definition. So, what I have here is from a short article to appear, hopefully, in Significance magazine of the Royal Statistical Society, broadly said. So, two definitions shortly that I mentioned. In the United States, citizen science was defined at the national level by Holdren as a process where the public participates voluntarily in the scientific process, addressing real-world problems in ways that may include formulating research questions, conducting scientific experiments, collecting and analyzing data, interpreting results, making new discoveries, developing technologies and applications, and solving complex problems. Quite lengthy and vague, I would say. And European Commission has used a definition from the Oxford Dictionary, defining citizen science as scientific work undertaken by members of the general public, often in collaboration with or under the direction of professional scientists and scientific institutions. It is often linked with outreach activities, science education, or forms of public engagement with science. So, as it includes, and very, very frequently, data gathering processes and data analysis, it is highly important for a statistician to ask if using some common statistical approaches, I list just few very general ones, regression, classification, dimension reduction, or say correlation analysis, can be and how used with citizen science data. Traditionally, amateur experts participate in structured and or complex survey. Many citizen science projects are similar and are now characterized more contemporaneously by large-scale, more unstructured surveys in general, and even other surveys. So you will hear more later. Increasingly accessible technology and devices, along with AI and machine learning, are being used to complement the process of gathering data by amateur experts, by everyone, which is the essence of citizen science. This has many positive implications for engaging people with nature. Most of the citizen science projects frequently come from natural sciences, ecology, biology, and this has led to more complex landscapes of projects and biases. So, what is a key issue? And this meeting conducted in framework of the Royal Statistical Society, and a special issue was that such data are naturally gathered by volunteers, and this process of the design, statistical design of the study, is very incomprehensive, complex, super complex, and it is a highly challenging question how to model this, how to study this, because it features many possibilities of biases, and naturally if you have a biased data you have biased results. So at present, if you want to study this just by normal regression, normal classification methods if you wish, you would very likely get some result, but this result would be very high probability, likelihood wrong. So this is one of the essences of what we talk. This image, again from this short article, hopefully Significance that I mentioned, that I have written for Significance, shows it is from a work of Kashian of 2020, shows how complementary can citizen science be to more institutional based, one could say, more common quantitative surveys, quantitative data. This is an image, so I participated. I wanted to see how actually looks more proper, I would say, general citizen science research. So I participated, I think, 2 and 3 years back at the probably main citizen science conference to date by the AAPS, which is American Association for this. This is an image from the second of these 2 conferences. It's, I would say, quite large community of scholars, but to my impression, very unstructured. Most of the presentations were presentations of some initiatives, not of scientific work, but it is an interesting to see, it will be interesting to see how this evolvement of citizen science research will proceed. As you see, there are quite a lot of scholars engaged. So, now to proceed to analysis of citizen science data, one could legitimately ask, so when is citizen science data a good way to study a statistical problem? We will hear about 2 examples now shortly. We will not proceed them in enough details. One of them, which was awarded recently in Edinburgh in September, a poster prize, it studied gathering data on Scottish badgers, small animals. They were engaged, so the interviewers, in a stratified survey, adding to previous one conducted by professional interviewers. Volunteers were assigned their territories to gather the required badger data. Number of volunteers and their easier decisions to gather data allowed more broad access to data. So very frequently you meet situations where you need a lot of representation of some spatial distribution of units that you want to have in a sample, and volunteer gathered data allows data which are otherwise probably even impossible or very, very, very hard and costly to get. So, some results show that there is value in this data. The poster that is on the next slide features results which estimate, I think, number of these badgers, some distribution, and so on. And it comes to the conclusion that this gathering was valuable. For the Slovenians, now probably part of the past or a different present, in the times of the pandemic, we had an initiative called COVID Sledilnik. It was featured a lot here around, people know it. So again, a lot of scientists joined, one entrepreneur, Slovenian, and computer expert, one would say, who at the start of the pandemic started with some table, inserted some basic, very basic information on some pandemic measures, and then many scientists from different areas, particularly younger ones, joined him. I would say we formed a platform, and still there are data on the pandemic, now outdated clearly, and it is clearly citizen science data. It was impossible to gather in another way because of at that time it was legal restrictions. So again, the citizen science way of gathering data proved to be important to get important data. But interestingly, while there are studies naturally with such data, we needed them during the pandemic time. To my knowledge, never has any of these biases, correct statistical assessment, been used with this pandemic COVID Sledilnik data. So here you have again the image. So this led me, I was part of this Sledilnik in the pandemic years. Also, I got acquainted with a young French scholar, Geneviève Robin, who at the time researched also in methods for citizen science data. It was part of her PhD at the time. She used some low-rank approximations of high-dimensional objects with matrix completion methods that Betsy, I assume, at least would know about. And an idea when I began as member of Royal Statistical Society's discussion meeting, and they needed a topic for a yearly meeting. I proposed citizen science data, analysis of citizen science data, and this led now to the great multi-paper discussion meeting. You even have now the YouTube recording and a special issue with 3 articles with a proposer, seconder. Seconder was Gary Mangerson, a renowned statistician from Australia, and interesting discussion responses from some leading scholars in Bayesian methods, in extreme value theory, and so on. We had 3 articles. Emily Dennis presented, we will hear about them today, and co-authors presented illustrations of computationally efficient methods for fitting new models applied to some major citizen science data sets for butterflies. What was of interest to these authors is computational efficiency. Another article that will present studies the same view on citizen science data and correcting for biases. Betsy and Peter Hoff presented a non-parametric, this means a method without distributional assumptions on Gaussianity, normality, and similar framework to obtain precise prediction sets for citizen science data based on indirect information complementing general, what they label direct information. Betsy will explain it. And the third article by 2 extreme value oriented scholars, extreme value analysis oriented scholars, Jonathan Koch and Thomas Opitz, developed a spatial temporal Bayesian hierarchical model for bias corrected estimation of arrival dates of the first migratory bird individuals at their breeding sites, with an interesting usage of extreme value for accessing some parameters there. This is an image that is now on YouTube of our meeting that we had in Brighton, and we continue this with another special session on this year's conference in Edinburgh with 3 scholars. Maybe we touch this at the end. It was again very, very interesting, and again showed that it is very important, as in this meeting in Brighton, Gary Mengerson pointed to respect, I would say, citizen science data, respect in the sense that the features and the biases are properly addressed. Some presentations had it, some didn't, and it was very interesting because it is an emerging study to discuss how to proceed here. So if you want to use such data, a very simple thing, a statistician might tell you to be really careful because understudied biases can bring the results wrong, and it is urgent to provide solid methodological responses ahead of just trusting without any solid knowledge the statistics, the calculations in such results. Okay, before I give the word to Betsy, shortly, I will try to skip a bit of this. I prepared a presentation. Actually, the literature that is emerging, as I mentioned, features, to my knowledge, only about 10, 15, Betsy can correct me if I'm wrong, articles at present. There are articles that I will not touch about Geneviève Robin, Julie Josse, even Robert Tipshirani co-authored their article in YASA, Journal of the American Statistical Association. There are papers by Alex Diana, who was one of the presenters in the Royal Statistical Society discussion meeting in Brighton. Alex Diana and his group, I will say, study in particular computational efficiency, and already in this article from 2022, it was published in Biometrics, they presented some fast Bayesian inference proposal approach for large occupancy data sets of citizen science analysis. Namely, again, they start by some general explanations that robust measures of biodiversity change are vital for monitoring the varying state of species populations and for evaluating progress of conservation actions, and data from standardized schemes are used to produce estimates of species status. However, such data sources are limited taxonomically and geographically, and formal sampling may be limited in spatial coverage and therefore cannot always be used to appropriately measure changes in species distributions over time. Conversely, opposite to this, or complementary to this, opportunistic records of occurrence are often and increasingly available in large quantities for extensive geographic areas and time periods and for a wide variety of taxa. However, they are inherently biased. Pocock, that you see here, is another author very active in this area, and the data are typically presence only, where records only indicate where and when a species is seen, rather than including information on non-detection unless complete lists are recorded. So frequently such data are analyzed using occupancy models. I will not explain them. It's a statistical way to model species. As they allow for imperfect detection, data are not standardized, result from the submission and collation of records by citizen scientists who choose where, when, and what to record, and are available in large quantities. So modeling such opportunistic data sets, occurrence data of this type, need to account for spatial, for temporal, autocorrelation if you wish. So something that is a value in this moment is correlated to previous values in time or spatially autocorrelated. And in this case, Diana and his co-authors used Bayesian hierarchical models. However, naturally, they used it because it allows to infer the effects of site and time specific random effects. It is a spatial temporal autocorrelation that you model. Bayesian models are nice for this, but we all know Bayesian inference is computationally, usually, frequently very, very costly. And what they proposed is a fast Bayesian method to address this. So this fast inference is based on, they model this by a Gaussian process approach, and they propose firstly some efficient polygamma augmentation scheme based on the polygamma probability distribution for inference, and even more interestingly, they compare three actually approximations for the Gaussian processes, more computationally efficient, based on either low rank or sparse approximations. On one side, they have an approach they call CP, which is a normal approach, and on the other hand, they have a subset of regressors. This is a low rank, and on the other, nearest neighbor, Gaussian processes, which is a sparse approach. And they found out that this subset of regressors, the low rank approach, performs best. Here you have the hierarchical representation in 5 parts. Then, as I mentioned, it is a polygamma distribution, which is then put into the distributions used for the Gibbs sampler, which is used to compute the posteriors. And here, I will not go into more detail, but if you wish I can. And here are some distributions. The results that they have received based on the spatial and based on the temporal location. It is to the left is 1970, then it's 1985. In the third column is 2014, and finally it's 2014. So it's an illustration. Betsy, are you here? Thanks. So I propose some 15 minutes. I will ask you questions if there will be. Thanks a lot.
Okay, so it's echoing a bit for me. Okay, I muted the studio, so just unmute if you are going to speak and send a chat, maybe if no one can hear me. Okay. Okay, so thank you so much to Andrej for inviting me. I'm very happy for this opportunity to engage in this conversation again. As you were mentioning, any opportunity to sort of talk about the difficulties of analyzing these types of data, I think, are important. So today I'll talk a bit about this project from my time with my advisor at Duke, with Peter Hoff, on frequentist prediction sets for species abundance using indirect information, which we applied and focused on citizen science data application. So just a bit of a brief overview to restate a bit, Andrej, what you were saying. These citizen science data sets are increasingly prevalent, consisting of data gathered by volunteer-led sampling efforts. There are a number of ecological examples, some that I've listed here. PlantNet, iNaturalist, and eBird are quite popular. I have friends who contribute to them, and there are a number of research articles utilizing data from them to draw conclusions about biodiversity and species environments and the like. So these are really serving as a vital data source. And as you mentioned as well, these data consist of unique challenges that make a robust analysis difficult, and it requires thoughtful care when analyzing them. So I'll speak specifically about the eBird database. This is a database that contains observations of avian species gathered by citizen scientists across the world. I'll look at a specific sample from the state of North Carolina and the United States that I've plotted a sample size from my data set here. And as I mentioned a bit, this database is widely used in constructing and implementing conservation action and policy. And there's a number of challenging features, one of which is that there are unequal sampling efforts across different subregions. In this case, we'll talk about different counties. And through this project, we'll aim to summarize the data at the county level while making use of all available information, which includes data from neighboring regions. So to introduce a bit of notation, for a county J, we say we observe NJ birds that fall into one of K species. And this counts vector X can be modeled as multinomial with probability vector theta. So for example, if a single bird is observed, the counts vector X, which consists of a single element of non-zero, is equal to the probability of observing that first species, theta 1. So one way to summarize such data is with a prediction set. We'll label that A for an unsampled unit from a region. So this prediction set will be a summary of the empirical distribution, and it will have a frequency interpretation. And it will consist of species that we expect to see for this unsampled unit. And formally, the probability that this unsampled unit will be contained in our prediction set will be greater than or equal to some error rate, 1 minus alpha. And ideally, the prediction set will have a small expected set cardinality, or it will be precise. That is, it will only contain the minimum amount of species needed to maintain this error rate. So with calibration and precision, there tends to be a trade-off between having maintaining this nominal calibration rate or having a precise prediction set. And so to mitigate this trade-off, we propose a predictive method that has both calibration and precision properties. So we develop and formalize an order-based prediction approach that relies on an ordering of the categories, in this case, an ordering of the species of birds. And we prove that all conformal prediction regions based on a multinomial sample can be written as a function of such an ordering and the data. And we develop an indirect order-based prediction approach based on a multinomial hierarchical working model that allows for incorporation of prior information or auxiliary information. So this is one of the main theorems from the paper, and it just states that every conformal calibrated prediction set based on some observed data X can be written in this way given by equation 1, which relies on some ordering, this vector O, of the K species. So essentially, for any ordering of the species, you can collect into your prediction set some number of species such that the resulting prediction set will be calibrated. But this leaves the question of how to determine such an ordering, or what is the best or most appropriate ordering. So there are a few principled approaches to obtain orderings. One would be a direct approach that only uses data available in the sample. So in this way, you would order the species based on your observed counts of those species, such that species with a higher observed count would be more likely to be contained in the prediction set. Alternatively, we could use an indirect prediction approach based on a Dirichlet prior with some prior parameter gamma. And then the ordering of the species is determined by the sum of your observed counts and this sort of prior pseudo count gamma. And in this way, we can incorporate auxiliary information. Sorry, I thought I froze for a minute. Auxiliary information into the construction of the prediction set. And there's an R package available on my website containing a procedure to estimate this prior hyperparameter gamma from auxiliary information and implement the direct and indirect approach that we propose here.
Interrupt you.
Okay,
You hear me?
so getting to back to the eBird data set, I wanted to share a bit about the geography of North Carolina because it's a bit unique. There's a number of different microclimates. So there's a coast on the east, a quite temperate region in the middle of the state here, and then on the west coast, there's a mountainous region with pretty high elevation. And so this results in a lot of different types of species of birds. So in total, in our sample, there are 393 unique species that were identified across the entire state, across 99 counties. And 50% of the species were seen quite infrequently. So 50% were seen fewer than 100 times each across the entire state. And some were seen much more frequently. So here I'm summarizing the data from our sample. Again, I showed this plot earlier. This is a plot of the log sample size. And within county, sample sizes vary quite drastically. So there are about 50,000 individual birds identified in Wake County. That's this darker purple region in the center of the state. So this is a highly populous region of the state. The state county is in, the state capital is in Wake County. A lot of universities that you may have heard of, Duke University and North Carolina State University, the big state schools are in this county. And that's in contrast to the sample size in this small coastal town, county, Pasquotank County, where there were only 8 birds in our sample. And the human population of this county is 1/30 that of Wake County, so this isn't too surprising. But this does highlight the unequal sampling efforts across the state. So for each county, we aim to summarize the data available with prediction sets. So we'll construct a direct prediction set that uses only the data from that county, and then an indirect prediction set using our method that uses data from neighboring counties to estimate that prior hyperparameter gamma in an empirical Bayesian way. So both sets will be calibrated. They'll have guaranteed at least 95% coverage, but they will differ in their precision and this cardinality of the prediction set. So the direct sets tend to be much larger than the indirect sets. In fact, they're trivially large. In 10 of the counties, the direct sets contain all of the species in our sample. So it's not very informative to say that we're 95% confident that the next bird we observe will be one of the species that we've observed in the entire state. So it's not too useful. And so here I'm plotting the empirical probability masses of species in one of the counties, Robeson County, to sort of highlight how the ordering comes into play in constructing the prediction sets. So blue bars are the MLE, and the red bars are the posterior predictive empirical probability mass for each of the species that were most frequently seen in Robeson County. So all of these species on the x-axis are contained in either the direct set, if their species name is in blue, the indirect set if the species name is in red, or in both prediction sets if the species name is in purple. So you can see on the right side of this plot, the species that have a high MLE and a high posterior predictive probability mass are contained in both the indirect and the direct prediction set. Then, and this plot is ordered by the posterior predictive probability mass. So then you have some species here in red where their posterior predictive mass is higher than the MLE predictive probability mass. In fact, these species have an observed count of 0 in Robeson County, but they were seen in neighboring counties giving this non-zero posterior predictive probability. And so that lends them to being included in the indirect prediction set over some of these other species here in blue on the far left of the plot that were observed in Robeson County, but maybe they weren't seen much in neighboring counties. So this is really highlighting the impact of the incorporation of this auxiliary information in constructing indirect prediction sets. So here's some more details of the percentage of birds observed within some of these, within Robeson County and neighboring counties of Robeson for these species that were not included in both sets. So the cormorant and kingbird were included in only the direct set, and the pine warbler and sparrow were included in only the indirect set in Robeson County. So again, here, this first row is showing the percentage in the sample of how many of these different species were observed in Robeson. So the pine warbler and sparrow were not seen at all, but the cormorant and kingbird were seen infrequently. So I think this maybe corresponded to a count of less than 5 for each of these species. But then these species that were included in only the direct set were very rarely seen in neighboring counties. Here, the cormorant was not seen at all in any of the 5 neighboring counties, in fact. Whereas the pine warbler and sparrow included in the indirect set were seen actually sometimes quite frequently, like here in this county. And so that corresponds to a higher prior hyperparameter estimate, gamma, which leads to the higher posterior predictive probability mass, and therefore the incorporation of these species in the indirect set. Okay, so thank you so much. I'll just summarize a bit. So in this work, we describe a methodology to construct frequentist valid prediction sets for categorical data that make use of information in neighboring regions or counties. And we show that utilizing this indirect information can result in smaller prediction sets overall. And the prediction sets maintain the same error rate across counties, which will allow for sort of a coherent notion of comparing across counties. And this is particularly useful in summarizing these data, which have unequal sampling sizes across this spatial domain, but we're interested in analysis at each of the subregions. So thank you so much. And thank you again, Andrej, for inviting me. I'm excited to continue hearing the rest of the talk.
Thank you. Thank you a lot, Betsy. Do you hear me, Betsy? Just verifying.
Yes.
Thanks. I have 2 short questions, if I may. As you know, I heard the paper, but firstly, you mentioned cardinality, of which it plays essential role, I think, in construction of your prediction sets based on indirect information. But cardinality depends naturally on number of objects there. Could this pose any problem in terms of different distribution that you would have within the sample, because cardinalities would probably change.
Right. Thank you for the question. I think
Thanks.
the cardinality of the prediction set, it is definitely related to the sampling effort and the sample size of the regions. So some of these prediction sets that have that are trivially large, that include all of the species, those are in these counties with very small sample sizes. And so it's hard to, say much in those cases. But that's where the incorporation of the indirect information is useful, so we can sort of gain power and information to reduce the cardinality by exploiting information in neighboring regions.
Okay, thanks. And shortly, just a second, which is more common
I
question.
muted you, I'm sorry.
Okay, thanks. Just another short one, and then we resume. A general one, you use Dirichlet prior. Could you use any other one instead of Dirichlet? Say, manure or any parametric other one?
Yeah, I think that's a really good point, actually. I'll mute you again. So we use the Dirichlet prior because of the convenience given the conjugacy, but I do think that there's space to utilize some maybe more complex relationship among the regions. In particular, you may expect that counties that are far away from each other, like counties along the coastline, for example, might be more similar to each other than a county to the west. So you want to sort of incorporate this complex relationship, and we could do that maybe with a different prior. That's a good point.
Okay, thank you. Thanks again. I will now... Okay, thank you. I will now briefly resume, and maybe at the end we shortly discuss also with the people from the network of citizen science. So, as Betsy knows, there were 2 other papers. I will shortly go over this at the Brighton meeting in a special issue on this topic in JRSSA. Firstly, another one from Alex Diana's group, Emily Dennis, Eleni Mateko, and Byron Morgan, who again constructed another proposal of an efficient approach to tackle butterfly data in this case. And this one that they proposed in for the special issue started from a Poisson likelihood expression for their data, which then basically what they add is they study this firstly in a concentrated likelihood form that you see here, where they focus on parameters alpha here, and secondly they add 2 previous approaches which used mainly Markov chain Monte Carlo patient context with variational inference, which is known to provide some computationally easier and sometimes better results, and this is what basically they add, and they gathered some nice results. The third paper at the special issue using citizen science data was by Jonathan Koch and Thomas Opitz. What they did is they combined extreme value modeling of migratory bird data, where they used this extreme value to construct some parameters related to first arrival dates, and again with patient methodologies. So again they referred to some general issues of opportunistic nature of citizen science data sets, of quality of data, of the bias correction approaches, which they addressed, which are the main problems, which are the main biases there. By systematically adding pseudo-absence information to the data set, they obtained binary observations for each combination of the checklist and the species, and they estimated this using binomial likelihood. And as I mentioned, they constructed a extreme value approach where extreme value is used to get an assessment of first arrival dates, which they constructed as an optimization problem, and by this they somehow included these extreme value distributions and theory, namely generalized extreme value Jeff distributions, which is general distributions in extreme value theory that you see here, and they included this into a hierarchical system, again based on context of the four regression equations that you see here. One is based on Poisson, two is based on Poisson, one on binomial, and another one on generalized extreme value distribution, and then they again included Gaussian processes, Gaussian spatial process priors that you see here. They even included penalized complexity priors from the Bayesian literature, and they added to this another computational feature which isn't their computation and is very timely. Recently, Vecchia approximations for valid Gaussian processes, again based on some smaller subset of the original subset of estimation. So this is the more general scheme, which is more complex, I would say, in their estimation. As you see, they combined two different types of data sets, eBird and BBS. And some results that you see here for different bird species, which show you this is for great chested flycatcher, for purple martin at the bottom, and also here for the chimney swift. This their approach allowed them to get consistent, I would say, results and estimations for distributions of species that they estimated. So I went rather very quick on this to conclude and maybe have at least some brief discussion, because I do think while this is an emerging topic, also I would say that Betsy knows, also in the Brighton discussion meeting there were usual number of people. It was late evening, but still its number also of submissions was not that high this year, that its causal inference was about 3 times or 2 times higher number of submissions to the RSS call. So, but it probably, this citizen science data features, I would say, design that is probably very interesting and poses some statistical issues which could maybe even be foundational, I would say, on one. So I do not know of such usual, probably common now design that would feature so much individual heterogeneity and this interconnectedness. So a question also for statistics is how to appropriately model all this complexity, high heterogeneity in gathering in the sampling design to get correct assessments and unbiased, hopefully, estimations. So short conclusion is that it is a novel dataset type, while naturally general features, it connects them to participation of the public, which is essential for citizen science data, for volunteer. These data are prone to statistical issues and are biased if used uncarefully. So several biases that were addressed in the special issue were sampling biases, spatial bias, computational efficiency and cost, observer biases, and we addressed many questions at that meeting, but all the presented articles use Bayesian approaches. Is this some feature selection bias for the call, or is Bayesian somehow inherently linked maybe to the spatial temporal aspect or any other? Also, it would be interesting to use machine learning. It is very natural for this time that we live in. But you already feature conformal prediction in the construction of your confidence and credible intervals. And also in the seconders discussion at the meeting in Brighton by Gary Mangerson, Australian statistician, she noted that she stimulated further research because to her expression, to her saying on this discussion, there are even more wild citizen science studies with even more incomprehensible design, more loose, more unstructured designs. So it will be very interesting to explore this and study what exactly does it bring to statistics, and to get some results, some estimators, and maybe to discuss where basically this research line now leads. We live in times of machine learning, of artificial intelligence. How to connect it? This is clearly a much wider, perhaps a more wide-reaching machine learning and AI stream of research. But what is the future of this research? What to do here? I even figured causal inference for citizen science data, something clearly unexplored, but it seems with this network connectedness and individual heterogeneity to even this promise some interesting work in the future. Thanks, and I open the large floor joke for discussion. Thanks, thank you, Betsy. This is an image from Edinburgh. Betsy, if you're still here, are you here still?
Yes, I am.
Yes, yes. This is an image not from the session that you organized and I moderated, but from the conference itself. So we had another session,
Wonderful.
as I mentioned, in Edinburgh. Thanks. So, Q&A. Thanks.
Thank you. I'd have a comment. I do think it's um, a really good point about the computational concerns. I mean, there's so much available citizen science data, like even just in the eBird database. There are samples across the entire world, and at this point for many years, I think, every day. So yeah, considering the best way to make use of all of this available data, I think is really important.
But how to maybe make computational things? Will you eliminate by computational things biases based on spatial sampling, observer things? How to do this? How to combine it? Maybe, yeah, something to consider. Because it seems also very related to design, statistical design, right? This is probably the main issue here, because volunteer-based collected data brings a totally different design into the survey, right, into the analysis. So how to feature this? It's far from randomized. It's probably the very opposite of randomization. How to properly model this? It surpasses this discussion probably, but do you have any idea for your further work in this?
I'm not sure at the moment. I haven't been thinking about citizen science data too much for a bit. But I do think, to your point, that there are a lot of interesting open directions that, yeah, would warrant being considered. Yeah. There is this line of work, power predictive inference, PPI, that's sort of motivated by making use of a lot of available data and debiasing estimates that I think could be maybe something interesting to consider in relation to some of the unique biases in citizen science.
Maybe I have another question. Where's the best place that citizen scientists can get help on this topic? I mean, this is the first thing. If you're designing a citizen science project, where to get help on statistical analysis?
This is clearly a question for Betsy. What do you do in the United States?
I mean, I know a lot of there are a lot of statisticians that are quite active in the area, and so I think they would be very receptive to yeah, scientists reaching out. I mean, a number, Andre, that we know in the UK, for example,
Sure.
and I have some colleagues Becky Tang and others at some universities in the Northeast in the US here that are very actively working on these topics and these concerns. So
do you have any connections
they'd
in
be
the
very
United
open.
States? Do you have any connections with AAPS or with any institution for general citizen science, science, such? Do they contact?
I don't.
Okay. That's another.
And maybe I mean this your presentation was on a specific type of citizen science project. So there are many different citizen science projects that are maybe not so let's say statistically biased, because sometimes, I mean, or is it's in another way, because let's say I know about a project on roadkills. So if data sets are reported by a roadkill, that's another type of statistical analysis, not just by population or different things, but by traveling and so forth. That's totally different. And also there are certain citizen science projects that favors the unexpected, so that the data that was reported by citizen scientists is very important because it's new, it's unique, it's very valuable. So do you know such statistical analysis of maybe different types of projects?
Yeah, that's a very good point. I mean, even in the eBird data, this type of alternative biases are seen in that birders will be more likely to, they'll sort of go to places where there are these rare birds, and they'll be more likely to seek out rare birds to then identify. I think that there are some data processing techniques that can be used to account for some of these types of biases, and it's easier in like the eBird data. There are some sort of structured ways you can do this, and I comment a bit on it in my response to the discussion in the article. But yeah, it's definitely an interesting point considering the different types of biases.
Yeah, I will just say that it's also from the experiences of these conferences of AAPS and similar, it seems quite scientifically rather messy, I would say, area. Say these conferences, when I presented a bit more statistical methods like distensorial things, completion and so on, it was nobody really, I mean, it was a feeling that it's something still to enter their circles. They were receptive, but admittedly say that they don't understand a lot, but that it would be very needed. I got even acquainted with two people on LinkedIn from this area, which seem to be quite known scholars or younger scholars, but interested. They want to know more about this, so it's something, to consider. But it's a good question how to get, connect between modeling, statistics, and projects, say, in citizen science, or okay. Let's end, if you agree. Thank you a lot, Betsy. It will be recorded, so it will get a lot of audience. We will maximize
Thank
it.
you.
Okay, so thank you to all. Thank you to the organizers, to Mitja and the crew here. Great. Let's stay in touch. Some ideas, nevertheless, arose, hopefully. Thanks a lot. Thank you. Great day.